Just to give you a little bit of background, AdRoll is a multi-product advertising technology company. And basically, we have a bunch of customers, and for those customers, we want to show ads to end users. We participate in real-time bidding to buy ads. There are some users on the internet. There's an advertising exchange. There's some infrastructure that we have. We're 100% based on Amazon Web Services, by the way. How do we show them ads? When these users are browsing the web, going to some website, the ad exchange will be contacted as a result of that. And they will then contact each of the market participants, which includes AdRoll, to say, hey, do you want to bid on this guy or that guy or whatever? And we have an opportunity to bid. In order to actually decide whether to bid, they also provide some additional information, which lets us identify the user to some degree. So we're able to look up some information about each user, which lets us make a decision on how much we value an impression for that user. It's real time in the sense that we have to respond to these requests in a timely manner. Most ad exchanges have a hard limit of 100 milliseconds. So we have to receive the request, do all kinds of processing on it, validate our system, make sure it's healthy, find out what that user might be interested in based on some data that we pre-computed and stored. We have to do a lookup in Dynamo. We have to do all that and then return a response with a price in less than 100 milliseconds. So that's what real time means. It's also a pretty high volume system. I think the current global peak bid request volume is in excess of 500,000 requests per second globally. And that's from every exchange combined. This is just for the real-time bidding product. There's also non-real-time bidding products that we also manage. We are 100% based on Amazon Web Services. Like I said, we use Dynamo extensively. I think we're one of the top users of DynamoDB. We upload data to and pull data from S3. We use Kinesis. So yeah, we also use Lambda. We don't use Lambda on the real-time bidding side, but we do use it to make our lives easier in other areas, which I'm going to talk about today. There are 4 areas that I thought would be interesting to talk about where we're using Lambda today. Server housekeeping, and by that I just mean we have all these servers. We need to do things when these servers come online and when they go away. We have a server housekeeping tool that does that. Work, offload, and privilege separation. By that I just mean we have some system that is receiving requests for work to be done. It just hands it off to Lambda to actually do the work. Event fan out. And that's just when we upload data to S3, that results in events occurring, and we use Lambda to route those events. And finally, serverless control systems. On the real-time bidding team, as part of one of our safety systems, we actually have a component that is solely based in Lambda, and it reacts to S3 events, and its output is basically an S3 upload. That results in our system being controlled as part of like a feedback loop. So we control our real-time bidding product using Lambda. So I mentioned that we have a lot of servers handling a lot of volume, and by a lot I mean up to 1,000 is just an example. That number can vary throughout the day. This graph is from Datadog. It's the plot of our bid request volume over a period of a couple of days. And as you can see, it varies throughout the day. So when there's a dip in volume, thanks to auto-scaling, we will have fewer instances, and as volume increases, we get more throughout the day. When these instances come online, we want to take action. We want to set up ancillary resources that these instances depend on in order to function correctly. And it turns out, as I'll describe, that Lambda is actually a pretty good fit for this. With this system, as I said, we need to keep track of all of our instances. We need to have control over them. And for anything that we set up, we need it to go away when the instances go away. Since we're using auto-scaling, we can actually use this neat feature called lifecycle hooks. A lifecycle hook is basically something that allows you to take action while your instance is pending and before it actually enters into service. And similarly, when it's terminating, before it actually terminates, you have an opportunity to take action. And you can take pretty much any action here. Essentially, the lifecycle hook specifies a notification target for an autoscaling event. And along with that event, there's a lifecycle token, which your lifecycle hook handler can then use to complete the lifecycle action after it's taken whatever actions it needs to take. As an example of what this looks like, this is just attaching a lifecycle hook to an autoscaling group. And for this code, by the way, I actually created a public repo on GitHub under AdRoll, just with some examples of like a complete system that exercises what I'm describing here, server housekeeping, as well as something I'll talk about in the next section. Why Lambda? You don't have to use Lambda for this. You could have your lifecycle, your autoscaling event be sent to an SQS queue, which you have some server that is sitting around waiting for to process. For us, though, on the real-time bidding team specifically, we don't want to add more different kinds of servers to our system. Every time we add a new kind of thing into our system, which is different from everything else is there, it's additional complexity that we don't need. And we on the RTB team maintain our own infrastructure. So if something goes wrong and we're troubleshooting, that's just an additional burden on every team member to understand, okay, go check on this server now. So if we can avoid running servers, that's a good thing. And obviously that's one of the central promises of Lambda, so good fit. Secondly, if your code isn't running, then you don't pay for it. It may not matter here specifically, but conceptually, that's pleasing to me at least. If we have long lull periods where our autoscaling groups have no activity, which we do, we have several minutes all the time where nothing happens, then we don't pay. Again, with the serverless aspect, if we can shift the management burden onto Amazon, that's something less for us to worry about. It also kind of promotes a more functional style. And by that, I just mean instead of standing up some server which has some complicated internal state, you're just feeding events to your Lambda functions and they're reacting to them. And it's just simple to think about, I think. If you have a small function that just does one thing well, I think that's a good thing, as opposed to, well, the alternative. And you can run just about any code. It doesn't have to be in Python or JavaScript, although you do need a harness to run whatever code you want. But and in fact, one of our teams does run a pretty complicated C program that's launched using a Python Lambda handler to handle something, which I'll talk about later. I mentioned that when our instances launch, we have to set up ancillary infrastructure that those instances need in order to function. What we actually do is, what actually happens is the lifecycle hook will cause an event to be passed to an SNS topic. That topic is used as an event source for a Lambda function. That function then takes whatever actions it needs, and then finally completes the lifecycle, which lets our instances continue. What we do is create an SQS queue for every one of our instances. The queue name includes the instance ID, and when an instance wants to access its queue, it can just calculate its instance ID using the metadata service, so it gets the right queue. And instance IDs are unique per account, as far as I know. So this works. After creating the queue, we subscribe it to our command and control topic. We use a single topic globally to which all of our queues for all of our instances in every region subscribe. It works well. If we have some control system that needs to distribute an urgent message, it just emits it to the topic. It then filters out to the individual machines. So you might ask yourself, why do this instead of just having an SNS topic that all of these instances listen to? We could do that. I personally like this approach because you don't have to create an endpoint that's a public web service, essentially, for SNS to emit events to. This also allows us to have events be in flight while an instance is still coming online. If it was done with an SNS listener, if there were an urgent message and yet its event listener were not online or it weren't subscribed or something, it wouldn't get the message. So I think this is useful. After we create the queue and subscribe it to our command and control topic, we record the fact that our instance is alive in a Dynamo table of our live nodes. And this just contains our instance ID, the region that the instance is in, and then a subscription resource name. And we use that later to unsubscribe later when the instance goes away. So you don't actually need to do this necessarily. One reason that we record instances separately in a Dynamo table is because of API rate limiting. If you have a lot of different teams all using the same Amazon account, like we do, so some other team, say, could be querying the EC2 API or ELB API at the same time we are to get information about what instances are online. When that happens, that call can actually fail because you're rate limited. And the technically correct thing to do is back off with like exponential retry. But one of our systems was written with the assumption that it could always get immediately data about what instances are alive at any moment. So we actually take the union of this table and API sources. After everything has been set up, the Lambda function completes the lifecycle and our instances can proceed. If you have a setup like this, then this is basically what it looks like. As mentioned, we have a control system that can send events to our global command and control topic, which filters through to our SQS queues, which then go to our instances. On top of that, we don't actually do this, but I thought it'd be interesting to add. You could also have a control system that if it wants to distribute a message to an individual node, it can just look up the nodes in the table and then just route it directly to the queue if it wants to, not necessarily through the topic, which goes to all instances. Again, this is in the public repository on GitHub under AdRoll Lambda examples, if you want to look. This is just a Python Lambda handler. I greatly prefer using Python for Lambda functions, having written both in JavaScript and Python for Lambda. I personally don't care for callback-oriented programming. To me, it's much clearer what's happening here. You can look at it and immediately tell what's going on. So yeah, so here, the event that we receive is just a Python object, in this case, a dictionary, which contains records. Those records are basically SNS events. We handle each one if it corresponds to a lifecycle event, which we can handle. There are only 2 of these, but anyway, if it's one of those, we handle it. We pass to our handler the region, the instance ID, and then the context, which is just like the name of your Lambda function, how much time it has left to execute, and so on. When an instance is launching, as I mentioned, we create the queue, subscribe it to a topic, and then record the instance in our database. Again, very straightforward. We're just using Blotto 3, which is included in the Python runtime for Lambda. The only real gotcha is, as mentioned, we have queues that are subscribed to an SNS topic. And in order for that to work, you actually need a per queue policy that allows the topic to publish to the queue, which is what this is. Otherwise, we just name the queue according to the instance ID and then proceed as I already described. I mentioned work offload and privilege separation. So the scenario is you have a user for your application. They have work that they want to be done. They're submitting it to your system somehow. Your system should do the work and then return the result. For example, you could have a web front end, which is receiving requests, handling it somehow, returning the result. What if you want to add some resource-intensive process or some process which is less safe for some values of safe? It would be good if you could separate the execution context from the request context. And by that, I just mean your web handler, which is receiving the request to do the work, shouldn't actually do that work if it's risky or whatever, resource-intensive. You can hand it off to some back-end system. You could hand it off to Lambda. Why would you want to do this? I think it's kind of a natural fit for many uses. In our case, we actually have a system which is basically a form validation service. And a user can submit a URL, and our web handler will pass a request to Lambda to fetch the URL, evaluate its JavaScript, and then return some result. So yeah, we could have done that in our web worker, but it makes the system more complicated. There's other issues. Having components which are isolated is obviously, well, it's a good practice. It makes it easier to reason about what your system is doing. And yeah, for Lambda, your containers or sandboxes are basically mostly stateless, mostly ephemeral. They go away after some period of time. If you mess up your environment, it's not permanent. And if you're doing this, you essentially will have a microservice architecture. I mean, using Lambda is like the definition of a microservice. If your needs are simple, then the implementation is also simple. I'm not going to cover more advanced uses like API gateway, but because we haven't needed that yet. But what we actually do is just invoke the Lambda function from within our web handler. Scenario could be this. You have users submitting the work to your web front end. The web front end is invoking a Lambda function. That function can do whatever it needs to do. Your front end doesn't need to know. It could do the work itself. It could submit it to a system like what I described at the beginning, some control system which then distributes it to a worker, and so on. Imagine that you have a very important and compelling URL that you want to analyze, and you have some web application that's accepting such URLs. For this example, there's a demo Flask app in that public repository I created, which basically invokes 2 Lambda functions in order to handle such requests. In this case, it will invoke an initial validator, which basically says, yes, this URL is valid. For example, it's on a whitelist, it looks like a URL, and so on. It then returns the canonical form of the URL, which is then used in a second invocation to actually do some work. In this case, the second Lambda function is actually fetching the URL and then distributing it to a backend worker for subsequent processing. It's another Python module. In this case, we are again using bot03. Very straightforward. The payload is just a JSON blob, and then that will get passed through to the handler as a Python dictionary. Event fan out. So suppose that you have a system like what I've been describing, set of backend worker nodes or instances doing tasks. They're going to be uploading logs as well as results to S3. Chances are some other people are interested in that data. So how do you get that data to them? Our machines upload logs of different types which correspond to different kinds of events, and they all go to the same place on S3. They're partitioned by date and instance, and basically not everyone is interested in every type. So we have these different kinds of consumers. Our goal is basically to distribute relevant events to relevant consumers. As mentioned, our uploads are not partitioned by type. I mentioned that because with S3 you can configure an event configuration, which basically is different according to the prefix of the key to which the event corresponds. So we can't do that for this application. You could just use a single SNS topic, which then distributes events corresponding to all types of objects to every consumer. It's not the worst solution. I think it's somewhat wasteful for a consumer to see events that it's never going to care about. If you can precisely direct your events, maybe you can make your consumer code slightly simpler. If your consumer has to know about all of the event types and then discard what it's not interested in, it makes it slightly more complicated. Obviously, you can still do it, but if instead you're using Lambda, you could perhaps just make your consumer care about where its output is going to go, but just always process its input, for example. Although we're not using Lambda to actually process these, but only to route them, but just as an aside. And yeah, we have long periods of inactivity between log upload events. Our instances dump logs like every 10 minutes currently, and that's these periodic spikes as shown on the graph. For what this would actually look like with Lambda, you just configure S3 to invoke your function with as a result of an upload event, and then your Lambda function takes care of routing it appropriately. In our case, we re-emit events to a per event type SNS topic, as well as a set of SQS queues for some other application. And it might look like this. With this setup, only consumers of type A receive events of type A, and so on. Serverless control systems. So I mentioned that real-time bidding is high volume and low latency, and it's pretty significant scale. And when things go wrong, they can go wrong pretty quickly. As part of one of our safety systems, we have a control mechanism in place which can basically clamp down on our system's behavior. Adding a new server into the mix to do this, like I mentioned before, just complicates our system. We can get away with using Lambda for this, and so we do. With the setup that we have, as I mentioned earlier, we have a feedback loop. Our bidding nodes upload events to S3, those filter through, and then they make it to our control system, which then decides what to do based on the data that it's seeing, as well as data from other parts of our system. That then emits events to our command and control topic, which tell our instances what to do, or what not to do. I think the main thing that we actually do with this system is broadcast S3 key update events. Our control system uploads a control file to S3 and then broadcasts, take this file from S3 and use it. It's basically how it's implemented. We wanted the feedback loop to control worker behavior, and Lambda was a good fit. We didn't want to add a new server. It's been working well in practice for the last 5 or 6 months. As for the why of Lambda, I think I've already touched on some of these. A couple things specifically, though. On our team, we use S3 extensively. We also use it as an interface between our own systems as well as other teams. In order to talk to us, another team might upload a file to S3, which we'll handle in some way. I kind of like that approach. It's easy to inspect the state of the system and see what's happening, think about what should happen. Lambda is very easily configurable to react to S3 events, and our events are sporadic. Our controller only has to run after something changes. It doesn't need to just sit around, so it's event-driven. And again, with no server to manage, that helps a lot when things are breaking and we're troubleshooting. We don't have to worry about this, because as long as Lambda is online, our code is going to work. This is what our system actually looks like, our serverless control system. It's basically a set of different Lambda functions which are all composed together to cooperate. This could have all been done with a single function, maybe with different code paths depending on where its events are coming from. But the inputs to each of these functions is basically an S3 event. I like keeping things small. With small Lambda functions, it's easy to inspect and tell by inspection what's happening, what should be happening, as well as for other team members to participate if anything's going wrong or if modifications are needed. So yeah, it works well in practice. S3 upload events result in our functions being triggered. Some of these might be from our own system, its output. Others might be from other systems that are telling us, giving us information about what's happening. These other functions do their thing. They're basically filters. If you can imagine composing a command line, which is just a sequence of piped commands, I mean, that's kind of the philosophy behind this. The end result is, after our business logic has run, the results are then aggregated, uploaded to S3, and then using our command and control topic, our instances are commanded to fetch the updated control data. Everything outside of this square is our control system. Everything in is the rest of our system.